Okay, so we're going to learn quantitative changes in equilibrium, meaning that we'll calculate equilibrium concentration using ice table and something called the 100 rule, which I'll talk about a little bit later when we get there. Now, recall the equilibrium law that we learned yesterday. KEQ is just the products divided by the reactants, and you have to raise to the power of its coefficients. Also, pure solids and pure liquids should not be included in your KEQ expression. So today, we're going to learn how to use the KEQ as well as the ice table to solve equilibrium problems. All right, so before we get there, the reaction quotient, Q, is something that is very similar to KEQ. If you look at Q, the expression, well, that's identical to what KEQ is. The products divided by the reactant, okay, raised to the power of their coefficients in the balanced equation. So what's the difference? KEQ is called the equilibrium constant expression, meaning that all of the concentrations used in that calculation are equilibrium concentrations. All right, so those are the concentrations when the system reaches equilibrium. Q doesn't really have this limitation. For Q, you can have any calculation at any stage. It doesn't matter. So this is the reaction quotient, which is different from K. K must be at equilibrium. Q does not. So in a way, Q is a special, well, no, K is a special kind of Q. All right, it's just that it happens to be all of the concentrations at equilibrium. It's just like a square is a special kind of rectangle. A square is just a rectangle with all sides being equal. Now, why are we learning about Q? Because if you calculate Q using non-equilibrium concentrations, they will tell us in which direction will the reaction proceed in order to reach equilibrium. So if you calculate Q, okay, you sub in your numbers, and you're not at equilibrium yet. You want to see, so do I make more products or do I make more reactants in order to reach equilibrium? So if Q is greater than K, then you know that the product to reactant ratio is too high. You have way too much product. That's why you have a big number. So to reach equilibrium, you need to reduce your products and make more reactants, meaning that you have to shift to the left in order to reach equilibrium. And in the diagram, that will be the picture on the right. Okay, you have a higher Q than K. Well, you got to equalize them by producing more reactants and eliminating more products so that Q will equal to K, you will reach equilibrium. If Q is K, then that's equilibrium. If Q is less than K, then the product to reaction ratio is too low. You have too little product. You have way too much reactant. So in order to reach equilibrium, you need to make more product and use some of that reactant, okay? Which means you have to shift to the right in order to reach equilibrium. So the comparison between Q and K will tell you in which direction will this reaction proceed. Because you have a double arrow, you really don't know which direction is equilibrium. So this will tell you, just calculate Q. So let's actually do this for example 1. So you have a container at 450 degrees Celsius. Nitrogen and hydrogen react to produce ammonia. The equilibrium constant KEQ is 0.064, which is really low, which we talked about earlier. The equilibrium does not favor the products. So when the system is analyzed, you find the following concentration. Nitrogen is 4 moles per liter, hydrogen is 2 times 10 to the negative 2 moles per liter, and ammonia is 2.2 times 10 to the negative 4. Determine whether the system is at equilibrium, and if it is not, predict the direction in which the reaction will proceed in order to reach equilibrium. So is it equilibrium? If not, which direction should we go? To do that, we need to solve for Q, okay, and then we need to compare that to K. And the equation is the synthesis of ammonia from nitrogen and hydrogen. So if you balance the equation, 1 nitrogen plus 3 hydrogen is 2 ammonia. From there, you can derive the equilibrium constant expression. And then you can use that to solve for Q and compare that to K. So we're going to do that together. Q is equal to NH3 squared over N over H cubed. Okay, exactly the same you would do for KEQ, except this doesn't have to be at equilibrium. You take your numbers, you plug them in, you plug in the ammonia, nitrogen, and hydrogen, and you whip out your calculator and you solve this. You get 0.0015. That's your answer. That's Q. KEQ given to you in the question is 0.064. So that means K is actually bigger than Q. So Q is less than K. It means you have two little products. You need to shift to the right to produce more products in order to reach equilibrium. So therefore, the reaction will proceed to the right and make more products. Okay, do we have any questions on how to use Q to determine in which direction will the reaction proceed? All right, cool. This is not what we're going to learn. This is the appetizer to the main course. What I'm about to teach is the main calculation that you need to absolutely know. So we need to calculate equilibrium concentrations if you know the initial concentrations as well as the KEQ. Okay, and I've developed a strategy. If you just follow these steps, you're going to get the answers every time. You start with the equilibrium equation. Got to write the balanced chemical equation. From that, you can derive the KEQ expression. And also, using what you have in the question, convert initial concentrations to moles per liter if it's not already moles per liter. Because for the ice table in step 4, everything has to be in the unit of moles per liter. So you must convert to moles per liter before you can use the ice table. And then use X to represent the unknown changes that will occur. Next, you set up an equation to solve for X using the KEQ. And then finally, use X to determine equilibrium concentration. Now, I know there's a lot of steps, but when you get the hang of this, you will do this a lot faster. You can even skip some steps. But for now, let's do them one step at a time, and let's look at this example right here. You have carbon monoxide. Reacts with water vapor to produce carbon dioxide and hydrogen. The state really matters here. They're all gases. Carbon monoxide is a gas. Carbon dioxide is a gas. Hydrogen is obviously a gas. Water vapor, I wrote the word vapor in there on purpose because water could be liquid, solid, or gas. It's a gas because it's at 900 degrees, okay? The KEQ is 4.200. So the question gives you the KEQ. Calculate the concentrations of all entities at equilibrium if 4 moles of each entity are initially placed in a 1 liter closed container. So you need to calculate the equilibrium concentrations. First up, you have to write the balanced chemical equation. Okay, this is a grade 10 exercise. I give you a word equation, you write the balanced chemical equation. I did that in grade 11 as well. But in grade 12, I will assume that you have gotten that knowledge and you know how to do that. You have to write carbon monoxide, water, carbon dioxide, and hydrogen. You have to know what chemical symbols represent each of these. Put them together in a balanced equilibrium equation. Double arrow in the middle. Don't use single arrow. If you use a single arrow, you will lose marks. Okay, you need the double arrow. Everything's a gas. It matters. Now, why do I say that? Because I need to know whether it is solid, liquid, or gas. Only gas can be, well, gas and aqueous can be included in the KEQ expression. If you have a solid or a liquid, you don't write it in the KEQ expression. So in this case, everybody's a gas, so everyone should be there. You balance this, well, it's a 1, 1, 1, 1. Everybody's balanced, so that's quite easy. You have your equation here. Okay? Write the KEQ expression. Well, it's the products over the reactant. Since the coefficients are all 1, you don't have an exponent. It's all 1. So that's the KEQ. Okay, so far do you follow? You have to write the equation, get the KEQ. If you write the equation wrong, you will get the KEQ expression wrong. You will get the entire question wrong. Okay, it doesn't matter what you do with the math. If you get the initial equation wrong, that's GG for that question. So please make sure you get it right. All right, so step 3, you have to determine all initial concentration. The question says 4 moles in a 1 liter container for everyone. So that is 4 moles per liter for everybody. Okay, they're all the same. Cool. Now you take that and you draw an ice table, something that looks like that. You have the balanced equation on top, ICE 3 rows, and then you start to plug in the numbers. In the first row, initial concentrations of everyone, well, that's just 4. Okay, I'm a very lazy person. I don't do extra things if I don't have to, but I did put the 3 zeros after the decimal because of sig figs. I won't take out marks if you don't do that. All right, but I will take out marks at the final step. But during your work, if you don't apply the sig figs, okay, I'll pretend I didn't see it. But it's a good habit to write out all the sig figs as you work, especially when there could be rounding error. Now this time they're all zeros, so it doesn't really matter, but I still wrote them anyway. The change. Now here is the tricky part. How does it change? Well, we don't know, so we're going to use x. The problem is, do we add the x or do we subtract the x? Okay, you can have 2 approaches for this. One, you can do this properly, and the way to do that is to use q. Remember, q will tell you which direction this reaction will proceed to reach equilibrium. You compare q to k and to see whether it's bigger, equal, or smaller, and then you will know left or right. Q is very easy to calculate because everybody's a 4. You have 4 times 4 divided by 4 times 4. 16 over 16, that's 1. Q is equal to 1. KEQ is 4.2. Q is smaller than KEQ. It means it must proceed to the right. Okay, that's example 1. We just did that. But that's very annoying. I'm not doing that for every single question. So my favorite strategy is to straight up guess. Yeah, you heard me. I will guess that this reaction will proceed to the right. In this case, I guess correctly because Q does proceed it to the right. I'm going to write minus X for the reactant plus X for the product. You might be thinking, wait, why would you guess when you can solve this? See, because it doesn't matter if I guess it wrong. If I guess it wrong, I'll just get a negative value for the X. I'll plug it back in and it will just go back to the correct sign. You see what I mean? If I get a negative value, then I know I guessed wrong. It should be plus X plus X minus X. But okay, I substitute X. The double negative will cancel to become a positive. So in the end, it doesn't matter. So that's why I guess, because I want to skip that Q calculation. That's just annoying. But if you don't like that, go ahead and do the Q calculations and you'll realize Q is less than K. This reaction should shift to the right. So that's why you lose reactants to make products. Okay, did I make myself clear? In a lot of questions, you're going to have 0 for products anyway, so that's clear. You have to move to the right, but in this case, it's not clear. So I guessed. The coefficients for the x's are all 1s. It has to match the balanced equation, so it's 4 1s. To have the equilibrium, you add up the first 2 rows. For carbon monoxide, it is 4 minus X. Water is 4 minus X, and then it's 4 plus X, 4 plus X. You have this. So now you have the equilibrium concentrations. You just need to solve for X. All right, if you solve for X, you can solve the question. Just plug it back in. But how would you solve for X? Does anyone have a bright idea before I just tell you what to do? Well, it's not obvious, but there is something you can do. If you can write this as part of an equation, you can solve that equation for X. But what equation? Notice that X is found in the equilibrium concentration, that row. And KEQ is the equilibrium concentration. So KEQ, if you write the KEQ expression, products over reactants, you would get 4.2. That's what the KEQ is. The product, you have 4 plus x and 4 plus x. You have 2 of them, so squared. In the reactants, you have 4 minus x and 4 minus x. Again, you have 2 of them, it's squared. So now all you have to do is solve this quadratic equation for x, and then you will get the answer. That's a grade 10 math problem. You can, of course, expand this, move it over, and then do the quadratic formula, and you get x. Okay, that's the hard way. The easy way is just to simply take the square root of both sides. And if you do that, then it becomes linear. Now it's much easier. So you just move things around. I'm doing this very quickly because this is grade 10 math. You move that over to the other side, and you push everybody over to one side. You factor out the x. You isolate x. You should arrive at this. Okay, you see what I did there? And if you sat through advanced functions and calculus of vectors and you got here, you should not struggle with this at all. If you did, then you would have failed those courses. All right, so x equals to that ugly thing. Notice that I didn't calculate this. I didn't bother taking a calculator and calculate the square root of 4.2. Why not? Because that's a waste of my time. Sure, I could do that. Square root of 4.2 is like 2 point blah, 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 with a long decimal. Then I have to copy that entire decimal on the calculator because of rounding error. And then I multiply that by 4, and then I do the same thing. I'm wasting my time calculating a number over and over again. So I like to save it for one step. For 2 reasons. 1, it just saves so much time. 2, I won't make a rounding error. If you round too early, you're going to have an inaccurate answer. If your answer differs from mine, you will lose marks. Okay, so that's why I keep it. Problem. Now, 3 sig figs. I rounded to 3 sig figs because the next step is a subtraction and addition. It's not multiplication anymore, so I round to 3 because it should have 3 sig figs. You take your x, you plug it back in to your equilibrium equation. 4 minus x is 2.623. That is carbon monoxide. Water, same thing, 4 minus x, so it's the same number. For the product, carbon dioxide and hydrogen, you have 4 plus x, so 5.377 for both. All right, so at this stage, you're done. That's it. If you put this on the test, you will get full marks, no problem. Make sure you round to the correct sig figs. In this case, the last step is addition and subtraction, so 3 decimal places for everybody, and that should be it. 4 sig figs, 3 decimals. Now, the additional step, step 7, you can check your answer. If you plug all of this back into the KEQ, you should get 4.2 or something similar to 4.2. If you do, then you know you did it right. So let's check it. So put it back. You square the 5.7 divided by the 2.6. You should get 4.202, which is very close to 4.2. So the answer is correct. Do we have any questions?
On the last slide, I don't get how you got like 4.200.
Oh, why do I have 4.20? That's the KEQ.
Oh, okay.
KEQ is equal to the products over the reactants. I used the KEQ expression that we found earlier. Does that make sense?
Yeah.
Or any other questions? All right, cool. Okay, so go ahead and practice. Example 3, similar question. You have 0.5 moles of N2O4 placed in a 1 liter closed container at 150 degrees. The 150 doesn't matter. What will be the concentrations of N2O4 and NO2 at equilibrium? So the KEQ is given. Okay, I'll give you around 5 to 10 minutes. I'll try to complete this, and then I'll take this up. All right. Okay, so for example 3, the first thing you got to do is write the balanced equation. Okay, so this is a decomposition reaction of N2O4 into nitrogen dioxide, NO2. So you write this out in double arrows and you balance it. You need a 2 in front of NO2 because there's 2 in the reactants. Once you have the balanced equation, you can write the KEQ expression as NO2 squared over N2O4. All right, so after you get that, determine the initial concentrations of everyone. You start with 0.5 moles per liter of N2O4, and the question doesn't actually say anything about NO2 in the beginning, so you assume it's 0. All right. You set up your ice table. It's a really small ice table because you have 2 columns. You have 0.5 and 0. What about the change? You have to use X. See, now it's very easy to see you should add or subtract X. You have no products. That means it must go in one direction. You have to go to the right? You have to produce the products. So there's no way for you to produce more reactant because you got nothing in the product. So it has to be minus X and plus 2X for the nitrogen dioxide. Make sure you have the 2 because you have to match the coefficients to balance the equation. So at equilibrium, you have 0.5 minus X and 2X for the product. Okay, I hope you all got this. All right, so next, now it is time to write the KEQ expression and you substitute the numbers in. So to solve for X, it is 4.5, which is the KEQ, equals to NO2 squared over N2O4. Here is where bed mass comes into play. You need the brackets on the 2X. If you omit the brackets, you would have 2x squared, then it's mathematically incorrect. Because if you don't have the brackets, the 2 is not squared. With the bracket, you square both 2 and the x. So you must have the brackets. You have to square the whole thing. The concentration of NO2 is represented by 2x. All right, so please have the brackets. And then the reactant is 6.5 minus x. So it is time to simplify. I move the denominator over to the other side, so it becomes multiplication. And I just squared the right side, so that becomes 4x squared. And then I move everybody over to the same side, so this is equal to 0. Now it is time to bust out the quadratic formula. That's the quadratic formula. You learned this in grade 10, and I highly recommend you just memorize that. You technically don't have to because in the booklet I gave you, it has the quadratic formula on it. Okay, I wasn't looking for the quadratic formula. I just wanted to look for a booklet that had every single thing I wanted for this course. It just so happens to have it. If it didn't have it, I wouldn't give it to you because it's a grade 10 formula. It's very simple. You're expected, everybody in high school is expected to know that. I just memorize it for street cred. You don't want to have to just look on the data booklet every time. So here's the quadratic formula. Apply this formula to solve for x because obviously that's not factorable. So you put this in, and the quadratic formula has a plus and a minus. So that means you should have 2 answers. Okay, you carefully substitute A, B, and C, and you would get 0.375 and negative 1.5. There's only one equilibrium. Which one do I pick? Folks, what do you think? If you don't know how to answer that question, consider what x is. What are we really solving here? X represents the change in the concentration, right? If you just go back and look at the ice table, X is found in the middle row. X is the change in concentration. You subtract X from the reactant to make the product. Can X be negative? That's a tricky question. Can X be negative, guys? No one wants to answer? X can be negative in some cases, but for this question, x cannot be negative. All right, so you have to reject the negative answer. Now, why can't x be negative in this question? Well, let me just go back. Look at the ice table. You have no products, right? The only direction you can go is to the right. You're already on the far left. Okay, you have 100% reaction, 0 product. Like Karl Marx himself would be proud on how left you are right now. You can only go right. So if you go right, you must lose reactants, so subtract x. If x is negative, then the double negative will cancel to become a positive. You're saying that I'm making more reactants, even if I'm at 100%, which makes no sense. Okay, so in this case, we know for a fact that this reaction is going to go to the right, so x must be a positive value. You would then choose the positive value and reject the negative, so x is 0.375. Okay, is that clear, guys? You only choose one answer, always one answer, because there's only one equilibrium. All right, so you choose that one. You plug this back into your equilibrium equation to solve for the equilibrium concentration. So if x is 0.375, then dinitrogen tetroxide is 0.5 minus x, which is 0.13. And NO2 just twice that, which is 0.75. Okay, make sure that you round to the correct number of sig figs. For the subtraction, the 0.5 minus x, you follow the least number of decimal places, which is 2. If you double that one, you have to follow the least number of sig figs. I have 2 sig figs there, because there was a number that we used earlier which had 2 sig figs. So you round to the correct number of sig figs at the end. You're done. You check your answers. That's it. You want to make sure you got it right? Okay, you plug it back to the KEQ, 0.75 squared over 0.13. It's about 4.3. And given that the KEQ is 4.5, you're right. Does that make sense? It's not exactly the same, but it's within a range where the error is acceptable. Okay, so do we have any questions on the solutions for this question? All right, cool. Now, that was an easy example. And this does get more complicated. Solving a quadratic, it can be annoying, but it's very easy to do. Solving a cubic, on the other hand, is near impossible. So you could have imperfect squares, and also you can have polynomials with an order of 3 or 4, or even more. See, I know in advanced functions, you learn how to solve a cubic equation, how to factor cubics and quartics. And you just use the factor theorem, you find the factors, and you do long division, and you should get it, right? Well, you can't really do that here, okay? Because in advanced functions, all of the questions that teachers give you, they can all be factored with nice numbers. In real life, that's not the case. You're going to have a lot of decimals. You're not factoring with decimals, so that's not going to work. Some of you do have a powerful calculator. Your calculator should be able to solve any polynomial. Just plug it in. It doesn't matter what the power is. Boom, there you have it. But I can't assume that you have a calculator capable of doing this. So I'm going to have to teach you a little trick to simplify the cubic to make it a lot easier to solve. And this is called the 100 rule. You can use the 100 rule to simplify your calculation if it satisfies a certain condition. And the condition is, if the ratio of the reactant concentration initially divided by the KEQ, if that number is substantially bigger than 100, then you can conclude that X will be very small compared to the initial concentration. So you can just discard that. You can just drop it from the calculation for simplicity purposes. You might be thinking, but why? What's the reasoning behind this? Okay, so follow the logic here. KEQ is the position of the equilibrium. If you have a large KEQ, that means you have a lot more products than reactant at equilibrium, so most of your reaction proceeded to make the product. If you have a really small KEQ, that means the equilibrium favors the reaction. Like a 0.0 something. That means at equilibrium, in order to achieve equilibrium, you go from 100% reactant to like 99.9% reactant, like 0.01% reactant, and that's equilibrium. Because you have a small KEQ, the change you need to get there that's X. It is so small that nobody cares. Okay, like imagine you step on a scale, you want to measure your weight, you look down at the number, okay, that's my weight. You plug one hair, and then you look down again. Hey, your weight didn't change, but your hair has mass. It's just that mass is so tiny, it didn't really come out on the scale. The scale only gives you 2 decimal places. But that is so light, it's not even there. You just round it off. Okay, if KEQ is small enough, and your initial reaction concentration is large enough, and the ratio given is, if you divide them, you get a number bigger than 100, then X, the change to get to equilibrium, is so small you can just ignore that. If you do that, the calculation becomes so much easier. Okay, but whenever you use the 100 rule, you have to justify by testing the value. You can't just decide, hey, I'm going to use the 100 rule, I'm just going to do this. You have to, on the side, write down that, hey, I'm using this approximation right here, and here's my justification. You do the math. Oh, look, this is greater than 100, so I can do this. You have to tell me you did that. Okay, that's not very relevant because we're doing online tests, and I'm just marking the final answer. But if this were a handwritten test, I would be marking your steps, and you need to have the justifications. If you don't have the justifications and you just dropped X, I'm going to assume that you suck at math and you just dropped X for no reason. It's algebraically wrong. All right, so make sure that you tell me that you're doing the 100 rule and you justify it by performing the calculation. So let me show you an example where we actually use this to solve a problem. So example 4, at 2000 degrees, the KEQ is 6.40 times 10 to the negative 7 for the decomposition of carbon dioxide and carbon monoxide and oxygen. Calculate the concentrations of everybody at equilibrium. Into carbon monoxide and oxygen. So write the equation first. CO2 becomes CO and O2. You do the double arrow. They're all gases, okay, because they're all gases at 2000 degrees. Actually, a lot of things are gases at 2000 degrees. So you balance it. You have a 2 for the CO2, 2 for the CO, and 1 for the oxygen. So now write the KQ expression because everyone's a gas, everyone's included. It's CO squared times oxygen, that's the products, divided by reactant of CO2 squared. All right, so far this is identical to the previous questions. You determine initial concentration, 0.25, 0, and 0, because the question doesn't tell us you have any products, you assume you don't have it. So the first row will be 0.25, 0, and 0. The change, well, it's got to go to the right because there's nothing on the right and there's no way to produce more reactant because you're already at 100%. So it's minus 2x plus 2x plus x. Make sure you have the 2. The x's must match the coefficient of the balanced equation. You add them up. You add up the I and the C, the first two rows, to get the equilibrium concentration. You have 0.250 minus 2x And then for the product, you have 2x and x. Okay, so far, same thing as before, again. Now we need to write the KEQ expression to solve for x. So here you have it. Here's the KEQ. 6.4 times 10 to the negative 7, which is equal to the products divided by the reactant. So it's 2x squared times x divided by 0.25 minus 2x, the whole thing squared. So here you'd be like, oh crap, how do I solve for x? Because I have an x cubed on top divided by x squared. Yeah, that's not going to be fun. You could try to just expand and put it all in on the same side and try to factor that. You're going to quickly realize that is futile. You're not going to do it. Unless you have a really powerful calculator, then congratulations, you can just do that. But if you don't, it's time to approximate using the 100 rule. How do we do that? Well, I'm going to assume that 0.250 minus 2x is still 0.250. X is that small and makes no difference. Okay, I'm going to pluck one hair from my head. My weight is not going to change, okay, because the hair is very light. How do I justify that assumption? Well, I apply the ratio. Initial concentration of what I want to assume, the 0.25, divided by KEQ must be greater than 100, and I plug in the numbers, yes. 0.250 divided by 10 to the negative 7. That is like a million, okay? That's huge. So this is a lot greater than 100. This is a very safe assumption. So the assumption is justified. I can do that, no problem. So I plug this in. I can simplify to this. I could straight up drop the x from the subtraction because that is exactly the same as 0.25. That's my assumption right there. You see what I did there? I dropped the minus 2x. You cannot drop the x on top, okay? The assumption only works if you add or subtract. If you add or subtract a very small number, you don't really change your original number. But if you multiply by a very small number, you get a very small number. So you can't do that for multiplication. It does make a huge difference. So only drop the subtraction or addition. So you have this. Now it's a very simple question. Solve for x. Like anybody can do that. Just move everybody over to the left and then take the cube root on both sides. Put this in your calculator. Your calculator should be able to do this all in one step. If you have a calculator that can't, again, get a new one. Put this in. Boom. I'm leaving a lot of figures because we're not finished. So x is approximately equal to 2.1544 times 10 to the negative 3 moles per liter. Is that a small number? I say so. 10 to the negative 3 is quite small. So you can, again, check. Actually do the subtraction yourself. 0.250 minus 2x. What is that? That is still approximately 0.25 if we just round off the last digit. So this assumption holds true. All right, so you found x. Congratulations. You can now use x to solve the rest of the problem. So again, carbon dioxide is 0.250 minus 2x, and that gives you 0.246. There is a slight difference, but that slight difference is so insignificant. It's in the 1,000th digit in the decimal. All right, so that's not going to matter a lot. Carbon monoxide is twice x, so that's 4.31 times 10 to the negative 3, and well, oxygen is just x, what you found before. Round to the correct number of sig figs, and you should have the correct answers. All right, so if you want to double check to see whether you got them, put it back into the KEQ expression. You got, well, 6.6 times 10 to the negative 7, which is very similar to 6.4. It's within the realm of acceptable differences. Okay, the difference is not significant. We say that it's the same thing. Congratulations, you got it. So any questions regarding what just happened here? How do you apply the 100 rule? How to solve a problem with a cubic or even a quarter? Anyone?
Can you explain again why you only dropped the x in the denominator?
Right. let me just go back. So you drop the x in the denominator because it wouldn't matter. 0.25 minus a tiny number is going to be 0.25. You see what I mean? If Bill Gates loses $1, I don't think his net worth will be affected. You see, because $1 is a small amount of money. If you multiply, because the numerator is multiplication, x is a tiny number. If you multiply a large number with a tiny number, then you have a huge problem. You lose everything. If Bill Gates multiplies his money by 0.000001, he'll still be richer than me, but he'll lose a lot of money. But if you subtract 0.0001, nothing happens. You see, that's the difference. Addition and subtraction, if you add a really small number, nothing happens. If you multiply by a very small number, a huge thing happens. That's why you don't change the numerator, you only change the denominator. Does that make sense?
Yeah, thank you.
Yeah, the numerator is easy to calculate anyways, 4x cubed. So you don't really need to drop it. It's the minus x that's the problem. All right, any other questions?
So even in case of like they have a small numbers on the numerator, then we would do it backward. Like instead of changing the denominators for the example 4, then we would change for the numerator then.
Yeah, if the numerator has plus and minus x, then you would do that for the numerator. You would just do it for whoever has the plus and minus x, because that's really what's making the calculation difficult. Because you have to expand that and factor that in order to get the answer, which is impossible to do with decimals. If you just multiply, then it's very easy. Just divide on the other side. Okay, so it doesn't matter if it's a numerator or denominator, as long as you have a plus x and a minus x, you can use this approximation.
Thank you.
You're welcome. All right, so last example. Try this on your own, and I'll take this up. So hydrogen and iodine are placed in a closed container at 440 degrees. The temperature never matters. They react to form hydrogen iodide. So at this temperature, the equilibrium constant, KEQ, is 49.7. Determine the concentrations of everybody at equilibrium if 4 moles of hydrogen and 2 moles of iodine are placed in a 2-liter reaction vessel. Keep in mind, you can use the 100 rule for quadratics as well, because I personally don't like solving quadratic equations. You know, that's just a waste of my time. So I will use this approximation for every single question if possible. And in fact, when we learn about acid and base, we will actually use this for every single question. We're just going to assume that this can be done, because all acids and bases have low KEQs. So go ahead and try this one, and I'll take this up in around 5 minutes. All right, so with example 5, same type of questions. You have to calculate the equilibrium concentrations of everyone. So you write the balanced equation, first of all. Hydrogen plus iodine is hydrogen iodide. You got to know that H and I are diatomic, H2 plus I2, otherwise you will get the wrong balanced equation. All right, so we'll write the KEQ expression. Well, it's HI squared over H over I. All right, so initial concentrations of everybody, you will have 2 moles per liter, 1 mole per liter, and nothing for HI. So make sure you do the division. The question gives you moles and gives you the volume of the container. You got to divide those. So fill out the ice table. You have the first row with the 2, 1, and 0. Again, the products, you don't have any. So it obviously proceeds to the right side. So you subtract x from your reactants and plus 2x in your products, because again, there's the 2 there. So equilibrium is 2 minus x, 1 minus x, and 2x. Okay, so far so good. You plug this into your KEQ expression, and the KEQ is 49.7 equals to 2x bracket squared over 2 minus x times 1 minus x. So that's a quadratic equation. Because I'm lazy and I don't want to solve quadratic equations, I'm going to use the assumption, the 100 rule. I'm going to assume that 2 minus x is equal to 2 because x is going to be a small, tiny number. Subtracting it from 2 will make no difference. Let's check. So I take the initial concentration, which is 2, divided by the KEQ. 2 divided by 49.7. Oh, crap, that's a very small number. Okay, that's 2 over 50. That is 1 over 25. Oh, man, that's less than 1. So that definitely does not satisfy the assumption. So it is not justified. You can't use the 100 rule. So if you can't use the 100 rule, what do? Well, you just have to solve it algebraically as you would normally. So here goes, oh my Lord, I'm going to, expand the top and bottom. So I will have 4x squared over 2 minus 3x plus x squared. And I'm going to have to move the denominator to the left side by multiplying. And then finally shift everybody over. So I have 45.7x squared minus 149.1x plus 99.4 equals to 0. You have a quadratic equation. At least you can use the quadratic formula. So plugging all of that ugly number in, and you should get 2 values. Now, I don't understand why only the 4 is highlighted. In the morning, I changed nothing. That entire number was highlighted. 2.33 or 0.934. You get 2 answers, but there's only one correct answer. Which one is it? Anyone that got to this stage? You don't have a negative number this time, so they're both positive. There is another way to figure this out. Use the context of the question. Any takers? Again, what is x? X is the change in the concentration. Right? If x is that number, it is saying that the reactants lost that amount to make the product. How much reactant do we really have? For one of them, it's 2 moles per liter. For the other, it is 1 mole per liter. If you only have 1 mole per liter, can you lose 2.33 moles? No, you don't have that. So that wouldn't make sense. You would have a negative number for the concentration, which is impossible. Okay, so that means you have to reject the 2.33, and 0.934 is the correct answer. So always reject. Only have one right answer here. So now you plug that in. So 2 minus x is 1.07. 1 minus x is 0.07. And HI is 2x, which is 1.87. You round to the correct number of sig figs, and you're done. By the way, 0.07 has just 1 sig fig. That's a rare exception where 1 sig fig is acceptable because in the last step you subtracted. 1.00 has 2 decimal places. 0.934 has 3 decimal places, so your final answer should have 2 decimal places. All right, and it just so happens 0.07 has 1 sig fig, but too bad, we're going to go with that. Checking, you put this back into the KEQ, you get 46.7. Okay, that's a little different from 49. That's because I rounded. Okay, I shouldn't round when I do this, but no, whatever. That is within a small margin of error. If you actually include all the other digits, it should be a lot closer. So it's close enough. I'm going to say that's the right answer. And this will conclude the lesson. Do we have any questions? Seriously? No? All right.